Mathematical software, and I've kind of settled on this title, Algebraic, Scientific, and Statistical Computing, an open source approach using Sage. So we're going to talk about each of these areas of computation, some algebraic computation, for example, working with multivariate polynomials, exact linear algebra, etc., groups, rings, and fields, that sort of thing. Then scientific computation, so working with floating point numbers, root finding, numerical linear algebra, those sorts of topics. And finally, statistical computing, so we'll do about little under 2 weeks of statistical computing. And this will mainly be about how to use R and related tools. First, does everybody have a copy of the syllabus? It should be going around. Is there a pile of copies somewhere? There's some, yes, so a bunch. Okay, so raise your hand if you don't have a copy yet. Here you are. So if you look at the syllabus, you'll notice that it has just some quick facts at the top, then a discussion of how your grade's going to be determined, some relevant textbooks, a related course. Somebody else who doesn't have the syllabus. And then on the back it has something which I hope you'll find very useful, which is a schedule. And I'll try to stick to this fairly closely. Although, of course, the schedule is so precise day by day that it's possible that we could change it slightly. But generally speaking, it'll give you a pretty good sense of when we're going to do what, and also what we're going to do in the course. So you can see the schedule is divided up into 4 parts. I'll pull the schedule up on the computer. So if you click, I'm not online. Strange. Okay, unfortunately I'm not online right now. But if you look at the schedule, it's divided up into 4 parts, or 5 parts, depending on how you want to count. Computing with Sage will be the first part, and that will be mainly about how to install Sage, which means getting going with the software, how to use it. You'll learn how to program in Python, which is the language that's used in Sage. And you'll learn about Cython, which is a compiled variant of Python, and how to debug programs, and also how to use a certain distributed revision control system, which is kind of like SVN, but distributed. So that'll be part 1. The second part, unfortunately, Wi-Fi isn't working. I guess I don't really need it. So anyways, that's part 1. Part 2 is going to be about algebraic computation. So groups, rings, fields, prime numbers, elliptic curves, public key cryptography, matrix arithmetic, exact linear algebra, that sort of thing. And basically each topic will get 1 day. And there's a lot of relations between the different topics. If you've never heard of a ring, don't worry. I'll define what a ring is. And also, if you're very much from the point of view of scientific computing, numerical computation, that's part 3, and you'll see a bunch of things about how floating point arithmetic works, interval arithmetic, which is something that Sage has extremely good support for, but most systems don't. Root finding, multivariate root finding, numerical linear algebra, finding eigenvalues and eigenvectors, that sort of thing, and also symbolic computation in the context of calculus. And then finally, the last part will be about statistical computing. So I'll tell you about the R project, about scipy.stats, which is a Fortran/Python-based library for statistics that's included in Sage. Both of these things are included in Sage. I'll talk about descriptive statistics a little bit, inferential statistics, and regression. And then finally, for the last 2 days, we'll have student presentations. And each day what I'll have, if you go to the schedule, which I can't go to right now because my laptop isn't authenticated correctly, but you'll see that the schedule looks a lot like what you have on the back of this piece of paper. But in addition, there'll be a link to something that looks kind of like this, which you can't see, but it's basically a step-by-step description of what I'll be doing in class during that day. So I'll only write that literally maybe minutes before class begins. But the idea is you'll have a record of roughly what we did each day. So that's the sort of thing you'll find on the website. So what I'll do first today, just to give you the outline for today, first I'll say a little bit about who I am, now that you have a sense of what the course is about. Then I will introduce some other people in the room. And I'll give you kind of a short, maybe 20 or 25-minute historical presentation about what SAGE is and where it comes from, along with a demo that illustrates various functionality. So if nothing else, at the end of today, you have a sense of the answer to the question, what is SAGE? Okay? After that, in the remaining about 10 minutes, I'll discuss further how your grade will be determined, things about homework, etc. So I'll go into a little more detail about specific things related to the structure of the course. Before I go on, any questions? Okay. Does everybody see, by the way? So I know that thing is in the way. You see? Good. I guess I can tell by just standing here. Yep, I can see. You probably can't quite see. I think you want to move a little to the right, or your left. So here's kind of a history of where SAGE came from. I was a graduate student at UC Berkeley in the 1990s, from 1995 through 2000, where a lot of software was written. For example, GIMP, the GNU Image Manipulation Program, was written at the same time when I was a student at Berkeley by 2 undergraduates as a student project initially, just to impress their friends. So if you've ever heard of GIMP, the GNU Image Manipulation Program, it's something that was just written by some students initially at Berkeley. But while I was there, I wrote something called HECA, which was a pretty big program for working with mathematical objects called modular forms. These are things that I won't say much about in this class, but they're really central objects in number theory, especially research level number theory. They played a central role in Andrew Wiles' proof of Fermat's last theorem. And really, a huge amount of the theme of research in number theory since about 1990 has been all about modular forms. So I wrote a lot of software for working with them. Unfortunately, I ran into an issue, which was that, well, I started writing an interpreter to make it easier to use the software I wrote for working with modular forms. And then I spent a lot of time working on writing fast, exact linear algebra. So by exact linear algebra, I mean something like the following. Say you're in a linear algebra course, and the professor writes down a little 3x3 matrix with integer entries. And he or she says, find the reduced row echelon form. So you sit there and you toil away with the matrix for a while, the numbers get really big, and then they get really small again, and you end up maybe with the identity matrix or something. But the answer is an exact answer. Or if the professor gives you a matrix like, wow, there's no chalk. But I can use SAGE to give you a matrix. Okay, there's a matrix, which you can probably barely see. I'll zoom in. So there's a 3x5 matrix, and a question in exact linear algebra would be to compute its echelon form. And there you can see the answer. And it could be a somewhat tedious process, and the intermediate steps as you go through computing the echelon form can involve pretty big numbers, and at the end the answer can also involve pretty big numbers and denominators and so on. And it's a problem that really a huge amount of mathematics ends up coming down to, computing various special forms of matrices. So in my work with modular forms, I started getting pretty frustrated because essentially everything I did at the end of the day boiled down to some linear algebra. And well, I spent a lot of time implementing fast linear algebra, but it just wasn't fast enough for what I wanted to do. And this guy, Alan Steele, who's one of the main developers of the computer algebra system Magma, visited MSRI, which is the Mathematical Sciences Research Institute in Berkeley, for about a week, and he taught me the system called Magma. Magma is it's not really commercial, but you have to buy it for about $1,000 a copy. And it's closed source, but it does linear algebra and a whole bunch of other things involving group theory, combinatorics, graph theory, and so on, very, very quickly. In particular, way, way, way more quickly than the code that I had written. So I ended up switching to using Magma specifically because of the very fast exact linear algebra that was available there. And I ended up writing a lot of code in Magma that was subsequently included in Magma. I worked for them as a developer for a couple of, well, I developed for them for about 5 years, but I visited them for a total of 3 months in Sydney, Australia. So I got a lot of experience in a sort of, I don't know, I guess, somewhat professional programming environment doing Magma coding. But at a certain point, I decided that the closed source development model of Magma and the ad hoc language, it has its own made up language. So if you look at computer algebra systems, there's MATLAB, which isn't really a computer algebra system, it's a scientific computing system. There's Mathematica, which is definitely a computer algebra system. There's Maple, there's Magma, then there's a couple of other systems like Maxima and Axiom and Derive and Reduce, and so on. Actually, who here has heard of more than, say, 3 of the ones I just mentioned? But wow, quite a few people. So there's a lot of these different systems, and one thing they all have in common, every single one of them, is they all have their own languages. So you know, like Java is a programming language, or Python's a programming language, or C is a programming language. Every computer algebra system I just mentioned has its own programming language. And that has its pros. You can argue at length about how good it is to have your own programming language, because you can say, well, it's amazing because it's, you know, designed for mathematics, so it's extremely easy to express mathematical concepts in this language. And there's definitely some truth to that argument. I mean, there's some validity to that argument, but there are also a lot of drawbacks to having your own language. Mainly that the people writing the system also have to be language designers. And the code written for that system, it's only mathematics code. Or if it isn't mathematics code, it's really badly written code usually. So I was sort of not so happy with that situation. So I would prefer, and a lot of other people would prefer greatly, to use a standard language instead of some special purpose mathematics only language. The advantage to doing that is that instead of restricting yourself to kind of the world of programming being just what happens to be written for Mathematica, you get what happens to be written for, say, C, or Python, or Java, or something like that. And in that case, you get a much, much, much wider range of code to choose from that's already out there, and functionality. Plus, instead of the math software company having to be the people that create the language, you have, I don't know, you have kind of a group of serious programmers creating the language, which is nice. Also, there's a lot to be said, especially in research mathematics, for open source. So if you look at how research mathematics works, which is the main motivation for starting Sage initially, you write a paper and you state that you've proved various theorems at the top of the paper and various places in bold in the paper. Then you publish the paper. And people then look at the paper and they read the proofs of your theorems and they believe your theorems or not based on whether your arguments are convincing. If your arguments are sufficiently convincing, then you get your paper published in a journal. And I mean, that's just how things work. If you just said, hey, here's a theorem that I proved, I'm not going to tell you the proof, but please say I'm the one that proved it, and that's that. Oh, and by the way, if you want to use my theorem, you have to pay me money. That might have worked for people like Fermat in the 1600s, but it definitely doesn't work today because we have much bigger margins, and you can definitely, it's reasonable to publish things. But the situation with computer algebra systems, like Mathematica and MATLAB and Maple and Magma and so on, is that these guys write the systems, then they say, hey, here's a function that does the following, and they don't show you how it does the following, and they say you have to pay them money to use it. And it's certainly understandable that a lot of money goes, you know, it's nice that they can charge money so that a lot of money can go towards writing really good quality software. Unfortunately, it just really doesn't fit very well with the model of research mathematics. In research mathematics, you have a problem where you really, really, really want to solve it. You want to solve it so badly you're willing to spend 20 years of your life, say, solving that one problem. I mean, that's how a research mathematician will sometimes approach things. Right, Jim? Yeah, I mean, so if you think about the sort of person who's very clever, very, very hardworking, willing to spend 20 years trying to solve a problem, and you ask what sort of tools that they'd want to use optimally. This is a person that would very much want to use a tool that they can look inside of. They don't want to use a function that, the function either works or it doesn't work. If it doesn't do what they want, they're stuck. If they know that they can slightly modify the function to do what they want, they should have the option to do that. I mean, again, you have to think, some research mathematicians will say, geez, it would be really, really good if I knew this specific area of differential geometry. That might help me with this problem I'm working on. And they'll go off for 6 months and learn that particular specialized area of mathematics, just so that they have a better handle on some problem. That sort of person would also put the effort into looking inside a computer algebra system or a mathematical software system and modifying it to do what they want, just because they really, really, really want to solve some problem. And, or at least they won't. With mathematical software, it's not so much usually that it solves a problem for you. I'm not talking at all about automatic proving or anything, but very often what you need in order to solve a problem is insight. You need to know what theorem you should prove. And in order to do that, you often have to do a lot of computations. In order to do those computations, sometimes you have to tweak the software that you have to make it much faster. And if you can't do that, then you're stuck, and it's very frustrating. So I'm just one of those research mathematicians who will spend 20 years trying to solve a problem. And about 3.5 years ago, in 2005, I decided that these tools were not good enough for what I really needed. I mean, technically, they were not as good as what I wanted. So 3.5 years ago, I started a SAGE project. And the goal really is to create a system that rivals all these MAs, and it's open source. It's not free in the sense that it's costing, I mean, people are paying money to support the development of the system, though most of the development is voluntary. But it is free in the sense that anyone here can just download it for free, and you can look inside. All the software we've written is GPL compatible. It's licensed under the GNU public license or something that's compatible with that, or a GNU public license. So that's the history. So in February, I released SAGE. I was so seriously committed to this that if I had to write the entire thing myself, that's the way it would be, as soon as possible. But 1 year later, I ran a workshop at UCSD on SAGE, the NSF funded, and actually a lot of people started helping out after that because they really liked SAGE, even though it was still pretty preliminary. And then a couple of months later, I moved to University of Washington from UCSD, and I had a workshop here, and then another workshop at UCLA, and then another workshop at here at University of Washington in the Mechanical Engineering Building a year ago, and then another workshop at the Clay Math Institute. This is the institute that has the 7 $1 million Millennium Prize problems. There are problems like the Poincare conjecture, the Burchant-Sorensen-Dyer conjecture, the Riemann hypothesis, and so on. So by the way, there are 7 conjectures in mathematics, P not equal to NP, and so on, such that if you solve any one of them, there's an institution that will give you $1 million, sort of a motivator. They announced the prizes in 2000, and one of them, the Poincare conjecture was solved by Perlman, who I think turned down the money, interestingly, and the Fields Medal. There's a lot of media publicity about that last year. So then in November, in Bristol, England, we had another SAGE Days workshop. And we had one in UCLA at IPAM again, and one in Austin, Texas recently. And the next one will be in June here at UW, in the middle of the month, right after finals week. So we're having a bunch of these workshops. And this is going to continue on and on. I have secured funding for 3 workshops a year for the next 5 years. So there's going to be quite a lot of workshops. So here's the goal of the SAGE project. It's to provide a uniform, open source, high quality, viable alternative to Magma, Mathematica, Maple, and MATLAB. In short, it's something very similar to how Firefox is a viable, open source, free, high quality alternative to Internet Explorer. It's kind of like that. It has a similar flavor. I don't know, can anybody else think of another example of an open source project that is making an alternative to some famous closed source system?
Linux?
Linux, yes. An alternative to Windows. Or OpenOffice, alternative to Microsoft Office. And in a lot of cases, it nicely meets the demand of those systems. One sort of guiding principle in the project is we try as much as possible not to reinvent the wheel, but to reuse as many existing building blocks as possible. And we're very obsessed with automated testing of the system. We also try as hard as we can to make Sage itself easily modifiable by anybody and document the whole system. Obviously, we haven't succeeded in any of this yet, but we're trying very hard. We also have a bunch of mailing lists. So there's an IRC channel, #SageDevelop, and I don't have any chalk, so I can't write. It's kind of weird. But there's an IRC channel, so if you're doing your homework assignment and it says try to solve the following problem and you can't figure out how to do it, you can hop on IRC and maybe get a little help. So obviously on your homework, be a little careful because I'll be watching. But also if you just have questions, you can ask me live on IRC. And it's an extraordinarily active channel. There's always chatter going on there. As you saw, we have workshops, there's mailing lists. The mailing lists have there's Sage Support and Sage Develop, and each have about 400 subscribers right now. So when you send a message to Sage Support asking a question about Sage, nearly 400 people are likely to see that question, and maybe somebody will answer it. Here's a screenshot from December when Sage was, it appeared in most of the mainstream, or a whole bunch of the tech media. And, here's the Slashdot story, for example, which said, a new open source mathematics program is looking to push aside commercial software commonly used in mathematics education, etc. And this generated a lot of downloads. There were about, I think, over 10,000 downloads of the complete Sage system, the software, in 2 days, on the weekend when this article appeared. We also won some contests. We got first place in something called the Trophies de Libra for the best scientific open source software of the year. It's a French competition. So what is Sage? Sage is 3 things. One, it's a distribution of software, kind of like Red Hat Linux is a distribution of a bunch of open source software along with the core operating system. Sage itself is a distribution of open source software. So when you download Sage from the website, and the current version, by the way, is Sage 2.11, which we released yesterday. The binaries are being posted right now. When you download it, you get about 70 open source packages. It's available for Linux and OS X, and then there's a VMware image that allows you to run it under Windows. So those are 3 ways that you can run Sage right now. By the way, we do care very much about supporting Windows. If you look at the download numbers, Windows is the most popular target that people download Sage for. And it's not like we don't want Sage to run nicely and natively under Windows. It's just that we started by taking a whole bunch of open source libraries written by, in some sense, the previous generation of computational math people. Although many of these libraries are, of course, actively under development, but an example of one of the libraries we include is Atlas, the automatically tuned linear algebra software. Another example is GAP, which stands for Groups, Algorithms, and Programming, which is a major open source program for doing group theory and common charts and related things. So we took all these packages, but the thing is, many of these packages are developed almost primarily on Linux, and they don't work so well under Windows. So there's a lot of issues with getting Sage to run nicely under Windows. That said, there are people at Microsoft who would very much like us to have Sage work well under Windows, and about a week ago we did a contract with Microsoft. So they're funding development of a port of Sage to Windows. So if somebody out there, one of you right now, is a good Windows programmer and likes porting software or getting software to work, I can hire you to work on porting Sage to Windows. So let me know at some point as the course progresses if you're interested in this. But I do have money to hire EW undergraduates to work on porting Sage to Windows. Okay? So this lack of good Windows support is only a temporary thing. And by the way, I mean, you can use Sage under Windows via this VMware machine. It just uses a lot of disk space, but it works pretty well. But we want something that works even better. So that's one thing that Sage is. Just a bunch of software all combined together in a way that builds on a wide range of machines and works. 2, a new library of functionality. So if you take the union of all the nice open source math software that's out there, you find pretty quickly that it has huge, huge gaps in functionality, or, I mean, to put it bluntly, in many ways it just sucks. I mean, there's a lot of situations where it's just kind of pitiful how bad the union of all open source math software is at certain problems. One example is polynomial factorization, multivariate polynomial factorization. The situation's pretty bad. Exact linear algebra could be much better than it is right now. And I mean, there's just a lot of little things where there's no algorithm implemented, or there's nothing implemented at all to compute with some object that people care about. Or if it is implemented, it's a toy implementation, or whatever. I mean, there's a lot of situations where things just aren't as good as they should be. Or more precisely, aren't as good as they are in Magma or Mathematica or Maple or MATLAB. That's really where we're trying to set our bar initially, is to be a little bit better than some of those systems at doing various operations that are important in mathematical computing. So we're writing a lot of new code to fill in the gaps, and also to make it so that when you use Sage, you feel like you're using one clean, integrated mathematical software system. You don't want to have to think, geez, I wonder how I'm supposed to do this in Maxima, and then wait, how does gap make a for loop, etc. You shouldn't have to know anything about how to use gap or Maxima or any of these other systems in order to effectively use Sage. So a lot of the work that we put in here is making it so that though there is this distribution, you can completely ignore it when you use Sage. And you'll see that sort of thing when I show you a demo in a few minutes. The size of this, I mean, it's hard to measure the size of a code base, but lines of code, or source lines of code is possibly some measure. Well, it is a measure, maybe not a good one. But this code is about, I think, 250,000 lines of code right now. Something like that. Maybe 200,000. Between 200 and 250,000 lines of code. So this is all new code that I have written and many other people. There are about, I don't know, at least 70 people that have contributed code to Sage. And each 2 weeks when we have a new release, the number of distinct people who have contributed code to Sage is usually about 30. And it could easily be one of you if you are that sort of person. Oops. Also, in one, where it says a distribution, here we kind of did a nice breakdown of how much code is in there, and it's just under 5 million lines of code total. Finally, Sage has some interesting functionality that allows it to interface with almost all existing math software. And again, I'll show you some demos of this in a minute. So if there's a function in Mathematica that you'd really like to use right in the middle of some Sage program, and you have Mathematica on your computer, then you can use that function. That's the sort of thing you get from these interfaces. We use it a lot when, well, for example, maybe I'm doing some research calculation, and I've implemented 95% of the things that I need in order to do some calculation involving modular forms. But the other 5% is only available in Magma. Fortunately, right in the middle of my Sage program, I can call that functionality from Magma and see what happens. Also, it's very useful when you don't trust the output of a calculation. There are a lot of calculations you do where you just don't know whether the answer is right or not, and there's really no reason to double check. So it can, it's nice if you can just run the same calculation in another system and see what it does. If it gives the same answer, maybe that raises your confidence, and if it doesn't, then you get really frustrated, but at least you know to be paranoid. The interfaces are really useful now, and they're designed entirely for getting actual work done, not open math idealism. Okay, I'm going to tell you a little bit more about the programming languages that Sage uses. Most of Sage, that is the new stuff. If you look at the Sage code overall, that is that big distribution, a lot of it's written in C, some of it's written in Fortran, some of it's in C++, some of it's in Lisp, etc., etc. But almost all the new code written, well, all the new code written is in Python, Python, or C, C++, in one of those three languages. Actually, we have a little bit of Java code, which we use for 3D visualization in a web browser. But we don't use Java too much, despite it being a very popular language. So here are some quotes about Python. It's has anyone here heard of Python, besides earlier in my talk? Okay. Cool. So most of you have heard of Python, but not everybody. So Python, there's a bunch of programming languages out there. There's hundreds. And if you look at, say, the top 10, Python's one of the top 10, where top 10 is, of course, in quotes, because what does that mean? but there is a sense in which Python's a pretty popular language. So I'll just read a couple of quotes to you. Python is fast enough for our site and allows us to produce maintainable features in record time with the minimum of developers. So that's a quote from somebody at YouTube, which, you know somebody who knows somebody who knows him? Or something?
Yeah, I know someone who works at YouTube.
Okay, cool. And vouches for this guy not being a crazy. Okay, cool. Google's made no secret of the fact that they use Python for a lot of internal projects. Even knowing that, once I was an employee, I was amazed at how much Python code there actually is in the Google source control or source code systems. And there was a recent quote by somebody that in Australia that said that 15% of Google's code base is Python. They don't use it very much for actual deployed products. They use Java and C++ more. But for experimental systems and internal projects, they use it a lot. That's my understanding. And Python played a big role in making Star Wars Episode 2, which I'm not sure if that's good or bad, but it is useful. And you're going to learn Python in the very near future. So if you don't know Python now, you will probably know it in a week or two. And if you look at the Python website, the big, which I can't bring up because I'm not online, the big quote right at the beginning is, Python is easy to learn. So don't worry, it's not going to be really, really hard for you to learn Python. How many people here have learned some programming language at all? Anything at all? Okay, so almost everybody, but not everybody. So if Python is the first programming language, well, if you're in the class, you're going to learn Python. So if you haven't learned a programming language, you're lucky because it's a nice language to learn first. And generally speaking, people tend to like Python. It certainly has its pros and cons. And I'm not going to claim it's the perfect language, but it does work well as far as getting work done and being readable. And it has a lot of users, a big developer base. It's under active development. At least two of the main people who direct the Python project have good jobs that allow them to work at least half-time on Python, etc. Here's a quote that came out recently. This company that ranks programming languages declared Python programming language of 2007. And I won't say much more about that. Also, a very important thing is a variant of Python called Cython, which is really, in a sense, just compiled Python. And I'll show you again in the demo a little example of this. What it allows you to do is take some Python code, possibly change it slightly to declare data types, and then compile the result into, well, it turns it into C code, and then you can compile the C code using a C compiler. And the advantage of this is that you can write code where it almost looks like you're writing in Python, but the code is very, very fast. And this is critically important in Sage. If we tried to write everything in Python, Sage would never get off the ground. It would be really, really slow, nobody would use it, and it would suck. And I can give you 2 examples of that sort of situation with other pure Python math software. There's something called NZ Math in Japan, which started at the same time as Sage, and hasn't got very far. And one of the reasons is because they try to write the entire system in Python, just in Python, which is a very, very bad idea. Really, if you look at the architecture of Magma, probably Mathematica, certainly Maple, certainly Gap, a lot of these systems, what you have is there's a level of the system that's written in a fast compiled language. It's always C, or C++. I think it's always C, actually, in those examples. And then above that, you have some interpreter language. And a lot of the things that don't have to be blazingly fast are written in the interpreter language. So you kind of combine these two. For example, there might be some matrix algorithm where it says, take this matrix, say an algorithm for, a recent one I implemented was solving AX equal to B, where X is a matrix, A is a matrix, and B is a matrix. And A might be, might not have full rank, might not be square, etc. So there are various operations you do, and it's fine to do that in Python. If you say, ask for the rank of A, it's fine to do that in Python. To actually do the computation of the rank, though, there you need to write that in some very fast compiled language. So, if you're going to say, if the rank is this, then do this, else do that, that's fine to do in Python. The actual calculation of the rank you must do in a compiled language, or it's going to be insanely slow. So that's why it's important that we have both languages. By the way, the lead developer for Cython is a grad student at UW. So if you have questions or you're interested in programming language design or whatever, There's definitely somebody to talk to about it around here.
Which department?
Math. His name's Robert Bradshaw. He's a grad student. By the way, I looked at the enrollment sheet, and most people enrolled in this class are math majors. I think there's one ACMS major and I think 4 computer science majors. So just in case you're curious. On the other hand, the number of people on the enrollment sheet is a lot smaller than the number in this room right now. Okay, continuing on, I'll skip this. See it? All right, now I'm going to show you a demo. And then we're just going to discuss the grading and syllabus a little bit. Okay, I already showed you this. How do I want to do this? Okay, so see how this, actually I'll just do it in normal form. Okay, so here's an example of computing 2 plus 3 in Sage. Before I do too much more, let me explain what's going on here. In a console, I typed a command. On my laptop, after installing Sage, I typed sage space -i notebook. Let me zoom this in so you can see this. So right at the command line, I typed that. And what happened was, at the moment I typed that, it started a web server running locally only on my laptop and only listening to connections from my laptop. And then it said, point your web browser at this address. And then it actually, because it's all happening locally, it just popped up the web browser right here. And when I use this, what looks like a web page to type commands into Sage, the internet isn't involved. In fact, my computer isn't online right now. I'm not validated to use the network right now. But I'm able to use this. And that's why it says localhost up there. The localhost indicates that it's local to the laptop. So when you use Sage, either under Windows, OS X, or Linux, it looks exactly the same. It's always through your web browser like this. Although, just one quick remark, if you're a command line type of person, you can also use Sage from the command line. So here's an example of, I'm starting up Sage on the command line, and then typing commands. See? It's pretty fast at factorials. Do 1,000,000 factorial in 2 seconds. Let's see. That probably takes a while. It's taking longer to convert the answer to ASCII and print it out than to actually compute the answer. It's kind of amusing. So yeah, it's over 5 billion digits. So you can use Sage at the command line. One very nice thing about the command line is if you exit and then restart, it remembers what you did in the previous session, which is nice. And you can also edit at the command line. So if you're a command line lover, you'll probably really like this command line. Oops. Anyways, it's a very nice command line. Okay, so back to our story. Here's an example of expanding something. So that kind of gives you a sense of the computer algebra sort of feel that you have. And I'll show you some basic programming. Doesn't look so good when I'm zoomed in. Okay, so let me explain what's going on here. Here I've defined a function. Not necessarily, I'm not claiming it's a good algorithm. It's an algorithm implemented to show you various things. And now I'm going to tell you about every line that's here and really explain this in detail. I'll explain it in more detail on Wednesday and Friday, because really that's the goal of the rest of the week, is that you learn how to program in Python. But just pretty quickly, if you want to define a new function in the Python language, you write def for define, and you put a space, then you give the name of the function, and then in parentheses you give the input variables. And then you put a colon, and then you indent, and then you put the definition of the function. And that's it. That's all there is for functions. You now know how to define functions. There's not procedures and functions and intrinsics and all kinds of things. There's just functions. Right after the definition of a function, if you put a triple quoted string, then you can put whatever you want right here. And this is just documentation. It's completely optional. I put it here so I can remember what this function does, what it takes as input, what it gives as output, and so on. But again, this entire block right here is 100% completely, totally optional. And now here's the actual implementation. You put a hash sign for comments, and then the rest of the line is a comment. Here I assign the variable j the value 1. And then I make a for loop where I goes through all the elements of this list. This notation means the list of numbers from 1 through n. It's 1, 2, 3, 4, all the way up to n. By the way, this is a special extension that we have in Sage that's not available in Python itself right now. That one line right there, the little one dot dot that n thing. So for each I, going from 1, 2, 3 up to n, where n is the input to the function, if I is even, that is if when you reduce I mod 2, it leaves a remainder of 0, then we multiply j by I. And then when we're done with the for loop, we return j. And notice that everything in the for loop is indented, and everything in the if statement is indented, and there's a colon. And that's sort of the structure of every control block or control structure in Python. It's the thing that defines the control block, which is just a little short word. It's like def, for, if, or while. That's another one. And then some sort of expression, and then a colon, and then indented one level, everything that's inside of the block. And it's always like that. Everything's like that. There's also user-defined classes that work. Sorry. It just has to be consistent. You can indent any amount you want greater than 0. It just has to be consistent. Critical thing that's totally different than in a lot of programming languages. The indentation matters. If you don't indent, it doesn't work. So if you were to just take this entire thing and unindent everything, there's no way that Python would know what's supposed to be inside of the for loop and what isn't. Notice that there's no semicolon, or no braces, no begin-end statements or anything. And this is annoying to some people, very annoying to some people. So watch out. And it can really throw you off if you're really, really used to using a language that has lots of curly braces and stuff like that. Yes?
Is the difference between the triple quotes and the hash mark that the hash is just for one line and
yes.
the triple quotes allows multiple?
Well, the triple quote, the hash is completely ignored by Python. It's just a comment. This is an optional thing, but it has a little bit of extra value added. If I go down here, and I get ready to call this function, let me evaluate the cell, and I hit the tab key here, or if I do F question mark, I see everything that's in the triple quoted strings. Another really cool thing is if you do double question mark, you get to see the source code as well, which is pretty nice. And that works on a lot of different things. So there's our function, and then I can use it. So f of 80, this is the kind of even factorial of the numbers up to 80, etc. Okay, so now you see how to define a function, how to make a for loop, how to do a statement, and so on. So you've already learned about half of Python programming. The other half is a little harder. Here's an example of using Mathematica to compute 2 plus 3. And what you get back is basically a string. Here's an example of making a Mathematica object. So maybe I should explain what I'm doing here. So when you type A equals Mathematica 2008, the very first time this happens, it starts up a copy of Mathematica running. There's now one copy of Mathematica running on my system, and it's staying running. And now what it does is it sends to that copy of Mathematica, set this variable equal to 2008, and then it sort of saves that. And then here what it does is it calls the Mathematica factor integer command on that and gives you back the result. And you can use anything that's in Mathematica this way. The key thing here, though, is that we had Mathematica on the computer. If you didn't, this wouldn't work. The next example uses octave to make a random matrix, and it inverts the matrix, raises it to a power, and so on. So it's just another example of an interface. So interfaces are just these ways that allow you to use a whole bunch of other math software from Sage. By the way, the list of different things that there are interfaces to is given up here. So Sage has interfaces to Axiom, Gap, Peri, Cache, Lisp, Macaulay 2, Magma, Maple, Mathematica, MATLAB, Maxima, UPad, Octave, Python itself, and Singular. So a lot of different systems. Okay, so those are the interfaces. Here's an example of Python. So this is some Python code, and it illustrates, again, defining a function and then making a while loop. And a while loop is a lot like a for loop, but what you do is you put while, then some expression. As long as that expression is true, it does what's inside of the block. And this is doing bit shifting, dividing the number by 2, until it's 0, and then you return whether or not you got 1 at the end. This will tell you whether or not your number is a power of 2. So basically, it just checks to see if the very last binary digit is a 1. So that's a Python implementation of a function to tell whether something's a 2 power. And timing it, you see that the timing is about 1.74 seconds to run this function on every integer up to 100,000. Now I'm going to write exactly the same function, but using Python. To do that, I just put %Python at the beginning of the input cell. What that will do is it will compile it on the fly, load it into Sage, and then we can use it. The only difference I made was that instead of n just being an arbitrary Python object, it's an unsigned int. It's a C unsigned int, which means that this will be faster because it operates at C speed. Basically, you do arithmetic with unsigned ints much faster than arbitrary Python objects. The drawback, of course, is that you'll get overflows if you feed in invalid input. There's also, right, so it's now compiled the code, and now, see, it's 0.03 seconds, so the result's 58 times faster. On the other hand, it could give completely bogus results if we, see, that's bogus because of overflow. So you have to watch out. So the Python one gives the wrong answer, only because of overflow. Whereas here it gives the right answer. All right, I think I'm running out of time, so I will stop, and on Wednesday I will continue with this demo and then say some more about how the course will be graded, about the details of the course grading and so on. If you have any questions that are, really, really pertinent to you deciding whether or not to stay in the course or whatever regarding grading, just come and talk to me right now. Otherwise, I'll talk more about grading and so on Wednesday.